introduce Professor Oscar Lopez-Pamies. Oscar is Spanish, but I'm here, I'm going to do the introduction in English. Basically, Professor Lopez-Pamies' highest achievement in his life was that he was able to win, to beat Ferrero in a tennis court, and he is a top-notch world tennis player. And that's the reason, I guess, that he's from Alicante. He got a scholarship to go to the US. And he got a scholarship to go to University of Maryland. And then, besides playing tennis as a top-notch player, he did a double bachelor's in mathematics, applied maths and mechanics. And after that, he did a master in both things. And then he moved to do his PhD in mechanics, theoretical mechanics, with Professor Pedro Ponte Castañeda, that actually was here last week for a PhD thesis. And then he also got a double. I mean, he always get doubles and both in a degree, a PhD from the University of Pennsylvania and École Polytechnique, the top-notch school in France. And after that, he just got a position at the University of New York at Stony Brook, where he is now a professor there. And here in his honeymoon, I guess it delayed honeymoon. Delayed. After 1 year ago, but that's the reason he's here in Madrid, And then he was so kind to come over here and to give us a talk in the things, I mean, he has been working lately that are related to the work Javier and I have been doing with the recent PhD with Joaquin Moraleda that defended his thesis last week. And then he's going to give his talk in English because he doesn't know the terminology in Spanish, and because Sean is here, and then that's on.
Not in that order.
But of course.
All right. So thank you very much for the kind introduction and invitation. So so this talk is about cavitation, and let me go briefly through the outline. Basically, I will show you experimental observations and what is the theoretical interpretation of those observations. What are the existing problems and what are the open problems? And I will concentrate on the open problems. And for that, I will show you two new techniques to address these problems. So, in the 1930s, people were doing a lot of experiments on rubber because the automotive industry started to use it very heavily. And one of the experiments that they did, and the one I'm showing here belongs to Jen and Lindley, and the famous paper in 1958, is that of putting a thin disc of rubber glued to metal plates. And they apply tension to this structure. Now, because the thin disc of rubber is glued to the plates, the state of stress and strain in the rubber is not homogeneous, it's heterogeneous. And in fact, if you make the rubber disc very, very, very thin, what you can accomplish with that is a huge hydrostatic pressure in the center of the specimen. So this is a way to apply hydrostatic pressure in rubber, a cheap way. So doing this type of experiments, a typical curve that they observe, so S here is essentially the force that you apply to the structure as a function of the applied deformation. You see that you have an initial linear behavior, and at some point something happens. You have a very drastic softening, and well, eventually you have hardening. So when they got to this point, they heard something. They heard noises, like something was happening to the rubber. And actually, I haven't been there, but you know, other people say that it's very loud. And when they stopped the experiment there and they cut open the rubber disc, this is what they observed. They observed a bunch of holes appear in the specimen. And this is let's say, a picture of the specimen in the undeformed configuration before you load it. Okay, so this is the phenomenon of cavitation. Every time you have a soft material, soft meaning that you can apply large deformations, an instability where holes appear, may happen. And this, of course, happens when you have high hydrostatic pressure, right? All right, so how can we interpret this phenomenon? So theoretically, there are essentially two. Before I go to the theory, why is this important? For obvious reasons, once you have pores, these things may grow, may interact with each other, and then this may lead to failure, right? So to some cracks. Also, you can use, and this has been used for a while now, rubber particles in a hard polymer. And one of the toughening mechanisms of this hard polymer, now a composite, is that the rubber particles cavitate. And the cavitation takes care of the hardening of this hard polymer. All right, so basically these are the two main motivations. It may lead to failure, and of course it's going to change radically the behavior of the rubber if you have holes versus if you don't have. And you can use that mechanism not just because it is related to failure, but also to toughen polymers. And of course you need to understand this cavitation phenomenon. All right, so yeah, let me get now to the interpretation of this thing. As I said, there are essentially two theoretical ways to think about this. Well, materials are not perfect, of course. They contain imperfections. And then you could think of cavitation as the growth of an initially small imperfection. So even, you know, if you have the most powerful microscope, you cannot see these holes. You can certainly assume that they are there. And what is cavitation? Basically, well, you have a very, very tiny hole, and cavitation corresponds to the event when this tiny hole becomes of finite size. At some critical deformation, it becomes of finite size, right? So this is the growth of an imperfection. And of course, you already know that in classical linear elasticity, this cannot happen, right? If you have a hole of infinitesimal size, the hole in the deformed configuration will be also of infinitesimal size because it has to go linear with applied boundary conditions. But here we're interested in soft materials. This is a nonlinear material, and this certainly can happen. Now, another interpretation is a bit more mathematical, if you like. We can think of this as of cavitation as a non-smooth bifurcation. So, large deformations means that for a given state of deformation, you may have more than one solution, right? So you start with one solution, and at some point you may bifurcate. Now, if you think in that way, you assume a perfect material. At some critical deformation, you may encounter two different solutions, a bifurcation. A solution without a hole and a solution with a hole. And now, this bifurcation is challenging because, in general, when you deal with materials undergoing large deformations, or a continuum really, you enforce, in general, that the displacement field is continuous. Now, this bifurcation, you have to allow the displacement field not to be continuous, at least at some point, so that material can break, and then you can have cavitation. So that's why it's non-smooth. And then the non-smoothness is a very tricky one, right? So this proposal was put forward by John Ball in a famous paper of 1982, thinking of cavitation in this way. And this, slightly less general than this, proposal was put forward by Jan and Lidley in the paper that I show you with experiments. Okay, so now, very quickly, let me show you what is known about cavitation and what remains to be done. Now, what is known, let me start with the view of imperfection growth. If we consider a material that is isotropic, incompressible, right? So this is the first approximations for rubber-like materials. And we look at the problem of the shell. Well, and the shell has an initial spherical hole that is of some radius that gives you an initial porosity F0. You can apply hydrostatic loading to this shell, and you can solve this problem exactly. Basically, you can relate the pressure that you need to apply on the boundary to the deformation, the radial deformation that you get in the boundary, right? So this can be solved, and you don't need to solve the equilibrium equation, which is a nonlinear one. You just need to use the fact that the material is incompressible and isotropic, and you have radial symmetry. And if you do that, the pressure that you're required to apply to the shell to deform it, a stretch lambda bar, is given by this equation, right? And this phi is the stored energy function that characterizes the behavior of the material. So this is for any material, provided it's isotropic and incompressible. All right, so you see here that the pressure, of course, depends on the stretch, but also on the initial porosity. And, well, that's for any shell, right? Any size of the hole. Now you can take the limit of F0 goes to 0, and then you will be considering what happens with that infinitesimally small hole in this shell, right? That's the problem of cavitation. What happens when the porosity is infinitesimally small? You are interested in what happens with the hole, and you can follow it. You can follow what happens with the size of the hole by monitoring the current porosity, right? This is the initial porosity in the undeformed configuration, and this is the porosity in the deformed configuration. And you see that it's a kinematical relation because, again, the material is incompressible isotropic, so it depends only on lambda bar. Okay? All right, so we have this solution for the shell, and of course, again, as I said, you can take the limit of F0 goes to 0, and we can see what happens. Now, let me show you that in the context of a particular potential. The formula applies for any potential, but let me show you this classical Neo-Hookean, right? So this is probably the simplest valid model for a rubber. And so that's the potential. You can put it in the integral. In that case, the integral can be done analytically, and if you do the integral, take the limit of F0 goes to 0, the linear term in the pressure goes like this term. And then you have a correction of F0 to the 1/3. Right? You see that this is something that does not depend on F0. So when F0 is equal to 0, right? The entire thing is 0. Okay? So you have something here. And now let's understand what's that something. Now this is a plot of current porosity as a function of the applied pressure, right? Now, the material is incompressible, and you're applying hydrostatic loading, right? So therefore, if F naught goes to 0, this thing is going to be rigid, right? If it's incompressible, it doesn't want to deform, because the deformation that you want to impose is changing volume, right? So the only thing that can happen is the hole grows. The deformation that you apply on the boundary has to go directly to the hole. So let's see what happens with the porosity as a function of the applied pressure when we decrease the initial porosity F naught. So you see that initially nothing happens, the porosity does not grow much, and at some point it grows very fast, right? So the porosity has to be between 0 and 1. Now you start to decrease from 10 to the minus 2, 10 to the minus 4 the porosity, and this behavior is the same but becomes sharper. Eventually, if you go and take the limit of F naught goes to 0 plus, what happens is you have the porosity remains 0 all the way. So you apply pressure, the thing is not moving. Of course, it's incompressible, right? Not moving, not moving. There's a critical pressure at which the porosity starts to grow, right? And the critical pressure for a Hookean material under this type of loading condition is 5/2 mu, all right? And this correlates certainly well with the experiments of Jen and Dindley. They were their experiments. They were trying to have a huge hydrostatic pressure in the center of the specimen, right? And if you make those things, the disk very thin, then you can compute what is the pressure in that center of the specimen and see if it correlates with 2.5 mu, the mu of the rubber. And the experiments correlate certainly well. Okay, so very quickly, because I'm not going to talk about non-smooth bifurcation, you can do the same thing. And instead of thinking of a hole in a sphere, you say that the thing is a perfect material. And what you try to do is to minimize the energy. So you have some boundary conditions. You write the problem of elasticity as the minimum potential energy, right? So that the elastic energy required to deform the material is given by that formula. And the minimum is given by the deformation that gives you the minimum energy. And if you insist now on radially symmetric deformations and you allow the displacement field to not to be continuous at one point, at the center, if you allow that, and you carry out the minimization, this is a non-smooth minimization, you get the same thing. You get the same formula here, right? Here is already F naught is 0, right? So this is what was done by Ball, and he obtained the same result, right? With rather nice mathematical methods. He obtained the same result as looking at the shell problem, right? So in this case, for radially symmetric solutions and isotropic and incompressible materials, these two views of cavitation coincide. In general, it's not known if they coincide because, as I said, this is a very tough problem mathematically, so there are a lot of issues of existence and regular solutions and all these things. But anyway, intuitively, you would like to think that both of these results coincide, and at least for this case, they do. Now, let me briefly go through these open problems, and later I'm going to concentrate on cavitation as the growth of an imperfection, not as the minimization of an energy. So what's open about these problems? So yes, the thing that we know is that the material has to be incompressible and isotropic. So what happens when the material is compressible? Well, then you're in trouble because you don't know how to solve the shell problem exactly. Then you really have to go to the equilibrium equation, which is a system of you can write it as a nonlinear ODE, right, in general, for hydrostatic loading. But in general, you're going to have a system of nonlinear PDEs, then you're not going to be able to solve that. So compressibility. The material is compressible, you don't know how to do it. There's only a handful of materials, special materials, for which you can compute exact solutions by solving this equation. But in general, you cannot do it. Now, general loading conditions. Of course, materials are not subjected to hydrostatic loading. They're subjected to general loading conditions. And by having a criterion that depends only on the hydrostatic pressure, well, you're going to be off. And I will show results about that. So it's important that you allow for compressibility because materials may not be, in fact, they are not incompressible. They are nearly incompressible. So you need to understand what is the effect of this compressibility. You need to, one of the main things is to generalize this to general loading conditions. And well, there are other things that are not known. For instance, we were looking at the shell and we assumed that our imperfection was spherical, right? What happens if the imperfection is not spherical? And that's going to be the case in reality. You're going to have some weird shape, right? Is that deviation from a spherical imperfection going to affect the result? If you assume that you have a square or some other shape, are you going to have a different result for the onset of cavitation, right? That's something that needs to be studied. Also, there are other things like surface instabilities. Every time you have a free surface, you may have wrinkles. And there are many types of surface instabilities. And these may happen in tension. So if you have a hole that is small and it starts to grow, well, at some point you're going to hit that critical deformation at which you have a surface instability. If you develop a surface instability, what's going to happen with the post-bifurcated solution? Right? There's an interaction between cavitation and surface instability. And there are other problems as well. But this is just a list of the main problems. Main is compressible and general loading conditions. Okay, so let me now, I'm going to formulate the problem for a general loading condition for a general material as the imperfection growth, as an imperfection growth formulation. Okay? And then I will show you two techniques to try to solve these problems. One of them approximately and the other actually exact, but also approximate in some way. I'll show you. All right, so let me get more specific now. We're going to think of materials as, well, we have a solid, it's hyperelastic, and is characterized by a stored energy function, W1 of F. And F is a deformation gradient tensor. Right here I'm using standard notation. And in this solid, we are going to consider a dilute distribution of imperfections, a dilute distribution of holes. We don't need to say where they are or the shape. We have a dilute distribution. They're infinitesimally small. Okay? That's the problem of interest. And, well, this thing is going to be deformed. And regarding the holes, we can employ what we do in homogenization. We can think of this thing as a heterogeneous material, right? As a two-phase material, as a porous material, if you like. And the distribution of holes and their shape and everything, actually, all the microstructure information is contained in this characteristic function theta naught of x. So the elastic energy of this heterogeneous material is given by this formula, right? So theta naught is equal to 1 if x is in one of the pores. So that makes this equal to 0. So the total energy at x in a pore is 0, because the energy of a pore is 0. Right? You have a vacuum. And if theta naught, if x is not, if it's in the matrix, this thing is going to be 0. So the energy of the total of this heterogeneous material is W1 of F. Okay. Now, how about this theta naught function that characterizes the microstructure? One of the main things that we want, given that we're not going to know what it is precisely, but one of the things that we want to know, and it's actually computable, is the initial porosity. So, okay, we have a dilute distribution, and how much is given by the volume average of theta naught, right? So these triangular brackets are volume averages. That gives you, in a sense, the initial size, the initial sum of the sizes of the holes in the undeformed configuration. Okay, so in that problem, what we want to do is we apply a macroscopic load. This thing is going to deform, and we are interested in what? In the initial in the current porosity. We want to monitor the size of the holes in the deformed configuration. So initially, so let's say that here lambda is some loading parameter. We start at 0 and we monitor the current porosity. How big are the holes in the deformed configuration? Well, initially nothing happens. Nothing happens. At some point something may happen, and then the porosity grows to finite sizes, right? So what we're interested is, what is that F bar critical, right? What are these applied deformations on the boundary at which F is no longer 0? It becomes of finite size, right? That's the problem that we want to solve. More specifically, what we want to solve is for F as a function of applied loading, and is given by this formula here. The determinant of F bar is what you apply on the boundary. F naught, again, is the initial porosity. And here we have the volume average over the matrix of the determinant of F of x. What is F of x? F of x is the deformation gradient of the displacement field, right? That minimizes the total elastic energy of the problem. Basically, we are looking at a boundary value problem of a heterogeneous material, right? We apply some boundary conditions to this thing. It's going to deform, and we are looking for the field that minimizes this energy. That's the field in equilibrium. And once we have that field, of course, we can compute anything. And if we compute that particular average quantity, that gives you the current porosity, right? So we want to monitor F. So that's what we want to compute. Of course, this is not an easy problem, because W1 is non-convex. It has to be non-convex for physical reasons. And non-convex means strongly nonlinear, and you don't have a unique solution. And on top of that, you have to take the limit. After you are able to solve this thing, you have to take the limit of F naught goes to 0. So in general, this is hopeless. And in general, so what can we do to come up with approximations for this, right? Given that in general, we will not be able to solve it exactly. So let me now go into how we can generate approximations. Now, okay, so let me start with this new approach 1, a linear comparison method. And probably most of you are familiar with this term. And this is something that has been used to develop some homogenization estimates for hyperelastic composites. But in reality, what it is a variational technique that allows you to solve this energy minimization problem of any structure. Right? If you have a heterogeneous medium, this is a technique that allows you to compute an approximation for that elastic energy E and the fields, and as I will discuss, like the porosity, the current porosity. So let me not jump here. Let me start with the idea. I'm not going to get into details, just give you the idea. What is this linear comparison medium method? So the main ingredient here is to introduce a medium that has the same macrostructure as your material of interest, where the phases, in this case you only have one phase because you have pores, so you only have the matrix, is not characterized by this hyperelastic nonlinear function, right? But by a linear potential. Well, the potential is quadratic, so the stress-strain relation that you get from here is linear. And you can see that this is the most general type of quadratic potential. You have quadratic, you have linear, and you have scalar term, right? So this is like, if you like a Taylor expansion, but not really, because this modulus tensor is not the second derivative of the potential, but rather is a modulus tensor that you need to obtain from an optimization procedure, right? So the idea is, how can we develop or construct a material with a quadratic potential like this, such that we get the best possible approximation for our nonlinear problem, all right? And there's a lot of things behind this. I'm not going to get into that because that's not the point. But I'll give you the result, and I try to give you a little physical explanation of what it means. Now, if we make use of this idea and do some calculations, at the end we can come up with a formula for the approximation for the total elastic energy, and it's given by that expression there. You see that it depends on W1, the store energy function of the matrix, depends on F bar, that's the applied loading condition, depends on F naught, initial porosity, and F hat 1 and F bar 1. Now these quantities are related to the fluctuations and the average deformation gradient in this linear comparison material. So what you need to do is solve the problem, the same problem that you want to solve in reality, where the matrix is hyperelastic. You need to solve it now for the case where the matrix is this quadratic potential. All right? So now you have to solve a linear problem. Now, once you solve this linear problem, essentially this is what you want to do: solve the total elastic energy of a linear problem. This W is T now, is the quadratic potential. Once you solve this, you can compute the fluctuations, the average. Really, you can compute anything you want, and you can put it in that formula, and that gives you the total elastic energy. Okay? All right. Now, so the problem kind of reduces to solving now this homogenization procedure problem in this linear problem. A couple of things here. In reality, this is not linear. Why is not linear? Even though this is quadratic, it's not linear because in the kinematical set of admissible fields, you have a constraint that is the determinant of F greater than 0, right? That has to do with material impenetrability. And this is a nonlinear constraint. The determinant of the deformation gradient, right, is a nonlinear function. So this is a nonlinear problem. So even though everything is linear except this, okay, forget it. It's not linear. So that's difficult to handle. So what we do is we enlarge the set, okay? So we're going to get rid of that, and we're going to make the set of admissible fields larger, right? So we're not going to impose the constraint. So we have a larger set. And basically, we denote by that larger set K prime, no determinant. So now this is truly linear. And even though the stress and strain measures are non-symmetric, right? F is non-symmetric and the hierarchy of stress is non-symmetric. That doesn't really matter because it's linear, has major symmetry. You can solve this problem using Green's function methods developed by Willis, for instance, okay? Now, given that we have got rid of this J greater than 0, what do we have? Well, we have a larger set. So at the very worst, in the worst case scenario, we have a lower bound to the solution that we want. And it is also possible to look at if the solution that you obtain doing this thing has the determinant of F greater than 0. In that case, a posteriori you can check that the solution is the solution that you want. Okay? So in some cases, you're going to have exactly the solution that you want. In some cases, maybe pathological cases, you may not. But still you have a lower bound. Okay? All right. So that's the energy. And then, of course, you can compute the porosity, because the energy is what? Is basically some traces of the deformation, something about the deformation, right? So is the porosity, so is any average quantity. If you have the deformation gradient tensor, you can compute anything, the total elastic energy, the porosity, whatever you want. And basically this is a layout of a procedure how to compute these quantities that have to do with microstructure. I'm not going to get into that. I'm going to show you the formula. I'll show you the formula for the energy. I'm showing you the formula now for the porosity in the current configuration, and using this procedure of linear comparison. And you see that it depends on f hat and on f bar 1, things that we already know and we need to use to compute to solve for this total elastic energy. Okay, so now if we're able to solve this problem,